In this video, we're going to talk about how to decide whether you have no triangle, one or two triangles, when you might have multiple triangles, what equations to use to solve them, and hopefully this will clarify everything for you, basically summarizing the last few lessons that we've had. So in the first drawing here, I've actually got the first case that we ever saw in our notes, anything that was past the right triangle notes, and that's when we were given two angles and a side in between those two angles. This is one of the cases where you have only one possible triangle always. And let me demonstrate what I mean by that. When I'm saying that you have one or two triangles, it means that the given information has to be true for any triangles that you draw. And when we have multiple triangles, you're able to draw more than one triangle where the given information is still always present and always true. So if I go to move one of these sides and I say that there are two triangles, I should still be able to have this given information present. In this case, if I were to move any of these sides around, move them in or out, it's automatically going to change one of the given features and it will no longer match the described triangle given to me in the problem. So for example, if I'm going to move this side a little bit inward, you'll notice a couple of things happen here. This angle will no longer be 80 degrees. That already breaks one of the given features, and it's no longer talking about the triangle that was given to us in the problem. The second thing that actually changed was the length of this side right here. If this is 10 units, then this is no longer 10 units. And again, that was given to us. So whatever triangle we draw has to also have that information. That alone would not be an efficient or sufficient second triangle because it already breaks the rules. If I were to move a different side, let's just say that one doesn't work. Let's try moving a different side. If I move this one, I have that same problem. Maybe this length is 10, maybe it is, but this angle right here is no longer 30, and this one is no longer 80. So now I've formed another triangle, but it does not match the given information, so it's irrelevant to the problem. And again, if I try to move this bottom side inward a little bit, same issue happens as with the first one. That given side length of 10 is no longer present. So none of those are valid triangles that match the problem we are given. The only one that we could possibly have is the one that was drawn first because it fits all of the given information for that case. Now, what equation should we use? I always set up my law of sines and law of sines first and then use law of cosines if I have to. Now, this one, if you're just glancing at it, it doesn't look like we can use law of sines because we don't have any single ratio. But remember, when you have 2 out of 3 angles, you actually have that third one already there. You just don't know it yet. So once we calculate that third angle by subtracting from 180, now we do have one complete ratio and we can proceed with law of sines. Now the second case I'm going to show you is not necessarily in the order that we saw them in the notes. This one is a side angle side triangle. Now you may remember from geometry that that automatically means there's only one triangle because if two triangles have the same side angle and side, they must be congruent. So there's only one possibility. There can't be a second triangle formed. But let's see again why that might happen. If I go to move this one side in and see if that makes a second triangle, I've automatically changed one of the dimensions that was given to me. So that's no longer valid. That doesn't meet the requirements of the problem. Let me try that with a different side. Let's say I move this one inward a little bit and call this my new triangle. The only problem is I've again changed a dimension. That's no longer 100. So even though it has that same angle and the same side as the original given triangle, it's already broken some of the features and it's no longer related to that triangle we started with. And again, if I move either one of these other two sides, this angle is no longer 40 degrees. And if it's given information, no matter what triangle you draw, it has to meet that given information. Otherwise, you're solving a totally different problem. So this one cannot be modified in any way without changing one of the given features. So this one can only have one possible triangle. And again, if we set up our law of sines right away, you'll see, oh, we don't have one complete ratio because we're missing a side here, an angle here, and an angle here. And this time we can't solve that by solving for the third angle because we don't have two of them. So this is one of the cases where we have to use law of cosines. But again, you don't necessarily have to remember that or memorize the different cases. If you try to set up law of sines and it doesn't work, then you have to use law of cosines to solve. The third case that I have on here was one of the last ones that we saw in our notes. This is the one that is the side, side, side triangle. And this one I told you can only make one triangle, and we hopefully, well, I remember this one easier just because it's pretty distinct. It's just 3 sides. This one you have to use the law of cosines as well. And that's just because we have no angles, so there would be no complete ratios in the law of sines. Now again, if I tried to move any of these sides at all, you'll quickly notice that it changes the third dimension. Even though this one is still 10 and this one maybe is still 15, this one's no longer 13, and all 3 of those sides have to be exactly what was given in the problem. So if we move any of these sides, it automatically changes the triangle we're working on, and we're no longer solving for the given problem. So this one can only have one possible triangle. There's only one case where you have 2 potential triangles, and that's when you're given a side across from the angle and one of the sides next to the angle. That's the only time when you have that ambiguous case. And let's demonstrate even better. Now that I have a compass in my hands, I can demonstrate why we can make 2 triangles and why it's okay when these other ones were not at all okay. But let me rephrase or re-summarize this. If you've been given an angle, the side opposite, and one of the adjacent sides. If you were given all 3 sides, then you're back at case 3, and that's just an extra angle that you were given. But if this was all you were given, that's the ambiguous case. So let me demonstrate even better, now that I have a compass in front of me, how we can get 2 triangles from our ambiguous case. So first, I've got this one on the side. I think I've made up these dimensions, so they're probably not on your test review, but let's look at this one. This one, we've been given the side opposite the angle and the side next to the angle, so this would be an ambiguous case. We would have to figure out, could there be 1 triangle only, or could there be 2 triangles? And if there are possibly 2 triangles, then there are 2 triangles. It's either 1 or 2. There's not really anything ambiguous after that. Okay, so let's demonstrate. If I take this side length, which I've labeled as 12. It's not really drawn to scale, but it's definitely shorter than the other side. And let me zoom out a little bit. And I go to rotate it in. Notice I'm using a compass here, so it's not going to change the length of that side. No matter where I draw it, it's going to have that same dimension that I labeled 12. So I'm just going to draw a little circle around. Let's try to do this without moving that point. Okay, there we go. So I'm drawing in a circle which has a radius of 12. So any point along that curve has a length of 12 from this dot. So if we look for that dot and where that curve crosses the base, that line that we connect them with also has a side length of 12, just like that side length on the far side. Now let's look at this triangle that we've now drawn here. If I separate it out and redraw it again, this has 40 degrees, 18 degrees, and 12. That meets the exact given properties that I was provided at the beginning of the problem. I have an angle of 40, the side opposite of that is 12, and the side next to it is 18. So even though this is a separate triangle from that dark blue one, they both meet the given properties, and that's why there's 2 of them possible, because there are 2 triangles that I could build that still meet the provided information. I haven't changed anything about the given information, but there's 2 different triangles that we could build. So now we need to find the dimensions for both of these triangles, since they both could be the triangle that we were given. Now, if I go over here to this one, this is when the side opposite is larger than the side adjacent. Opposite is greater than the adjacent angle, or side, sorry. Over here, I didn't summarize this, but the opposite was shorter than the adjacent side, as you see. Now, when I go to do that exact same demonstration over here with this side length that is longer, get my compass in place. There we go. And I go to draw that curve. Paper's wrinkling a little bit, but you can see that that's pretty close. That bigger curve is a radius of 13, from this point. So again, if I look at where it crosses the base, just like I did before, and connect those dots, that forms a second triangle. So I'm going to redraw that triangle up there, just like I did over here, and write in my properties. So this little side right here is still 10. This one is 13 because I made it that way. But this angle has changed. That angle is now 140, which means this second triangle doesn't fit the properties that we were provided with the problem. So this is not a valid second triangle for this problem, because now that we've changed the angle, we're solving a completely different problem. So whenever that side opposite is longer than the side adjacent to the angle, it creates a triangle outside and changes your given angle. It's no longer a valid triangle. So the only time in all of these cases we looked at when you can have two triangles is when you are given first the angle, a side opposite, and a side adjacent. That told me that this was the ambiguous case. And then on top of that, if the side opposite is shorter than the side adjacent, that's when you'll have two. If it helps, I can provide a compass and you guys can draw the second triangle and see what happens. But you will be able to see, if you just estimate that side length, that this is going to come inside the triangle. This one's going to swing way too far out and create a triangle outside the one we were drawing originally, and that is not a valid triangle anymore. Now, of course, I'm making a little bit of an assumption that this triangle even exists. Remember, if you solve for this angle using law of sines and your calculator gives you an error message, then no triangle exists at all. So even if it could have been two, just because this one's way too short, that means that we have no triangle at all. So that's another consideration to make, but that comes after we've drawn these two. So again, if I go to do sine of 40 over 12 equals sine of whatever this label is over 18, and solve for that b, and my error, or my calculator gives me an error message, then there was no triangle at all. And even though there could have been two, it doesn't exist because this side is way too short to reach. All right, so I hope that helps. Of course, as usual, email me or message me if you have any questions about this or need any clarifications. Keep working on your test reviews. I'm hearing back from some of you guys. It's great to hear back from you and seeing some really good questions. So just keep me updated if you have any other issues or questions, and I'll make some videos and post them tonight. Thank you.